Okay, welcome to another quick mechanical science video. What we're going to look at today is something called direct stress. Now over the next few sessions we're going to look at direct shear stress, and we're also going to look at strain, elastic modulus and modulus of rigidity. So this is the first in a series of videos built around the same theme. So the question we've got today is in front of us. We've got a tie bar of length 2.4 meters with a diameter of 40 meters that carries a load of 50 kilonewtons. All right. Now, during your end of year assessment and also through the sessions, you'll have access to a formula sheet. Now, the formula sheet will look a little bit like this. It'll be a PDF, and on there'll be a heading that says stress and strain, and you can actually see there's a range of different formulas that fit within this category. Now, if we have a little look at the question that we've got, this word up here that says tensile and load, that actually tells us we're dealing with a direct stress calculation. So let's go back to our formula sheet and we'll determine that the formula that we're going to use is for direct stress. You see a little symbol equals force over area. Now don't get too hung up on trying to remember all the symbols, because you will be given the headings in the actual formula sheet itself. Okay, so I'm going to take that formula, I'm just going to drop it onto my little answer sheet. So stress is equal to force over area. Now if it makes it easier for you to remember the formula, you can write stress equals force over area. Nobody's going to be checking whether you can remember what that symbol's called or what where it fits into this. If you want to write it as stress equals force over area, then by all means you can do that. So let's have a look back to the question. Tie bar of length 2.4 meters. I'm going to make a little list here. Length equals 2.4 meters, a diameter of 40 millimeters, and a load of 50 kilonewtons. So when it says load, I'm actually talking about a force, 50 kilonewtons. Okay, now if we go back to our formula here, we see force and area. Now length, do we actually need that? Well, on this occasion, no. So we don't need to worry about the length. Although we've got it on our list, we don't need to concern ourselves. What we're going to be using is the diameter and the force. So let's have a little think about the units that we've got here though. So diameter equals 40 millimeters. Now the rule of thumb is in the 99 out of 100 science calculations, the units that you require when you're dealing with millimeters, you need to transfer them into meters. So what we'll have to do here is we need to divide this by 1,000. And that would look like 0.04. Now don't be scared to put that into a calculator. 40 divided by 1,000. The thousand's always a constant, although you might find it easier just to move the decimal point. Next one we're going to look at 50 kilonewtons. So we're going to rewrite that in standard form or engineering notation. 50 times 10 to the power 3 newtons. Okay, so let's go back to our formula. We've got force and area. So we can actually start to lay our formula out here. So we've got force, so we'll do stress equals force, which is 50 kilonewtons, 50 times 10 to the 3, divide that by the area. Now the area that we're looking for is the area of this, the diameter of this bar. So we'll remember from our GCSEs that area of a bar, a circle, is equal to pi r squared. Now we'll come over here, we've got diameter. We need to divide that by 2 to give us our radius, obviously. So we're going to do pi times, divide that by 2, which is 0.02 squared. Now, just so that we don't send any incorrect signals to our calculator, we're going to put the radius into some brackets. Now, when we put that into our calculator, and try and always use your division function on your calculator for that one. Don't lay it out sort of longhand. Use your division function. Makes it a little bit easier in the long run for applying it to different contexts. But what we'll find here is we'll get an answer of 3978, and the number goes on and on and on for quite a substantial time. But what I want you to do is I want you to hit the ENG button on your calculator, and what that will do is it will simplify this answer for us. And from there, what we can do is we can turn it into an answer of 3 significant figures. So what we'll find is we'll get an answer of 39.8 to 3 significant figures. And if we've hit our ENG button, we'll get 10 to the 6. Now, if we have a little think about the units here, we've got a force on the top, and we've got an area on the bottom, so we can use Newton meters squared, or the more common units that we use for stress is the Pascal. 39.9, sorry, I've got that run the wrong way, I'll just rub that out there. Go back to our pen, sorry about this, and we'll go to 39.8 times 10 to the 6 pascals. Okay, so we've got our answer for that question both in Newton meters squared and in pascals. Either one is correct. However, the more common units that we use for stress is a pascal. Now, we've got a solution to this direct stress question, 39.8 times 10 to the 6. So what I want you to do now is I want you to just have a little look at this next question, and I want you to have a little go at that yourself. Now, feel free to work it up, take a picture, send it to me through Canvas, and then hopefully you can start to build up a bit of skill and experience in solving these problems over the next few sessions. And I look forward to working with you on the next bit of this journey. All the best, take care, bye.